All right, this one's for all you football fans out there. Let's calculate the final velocity of a football player after a collision. Travis Kelce, the Chiefs' 118 kilogram tight end, is moving with a speed of 6.15 meters per second when he collides with Chargers safety Derwin James Jr. If Kelce experiences a resistive force of 831 newtons over a time period of 1.30 seconds, then let's determine Kelce's final velocity or final speed. Now, again, our expression looks the same. I'll write our impulse momentum expression again. All right. Now, this problem is a bit more complex because we're looking for a variable, his final velocity, that is not explicitly in this expression. However, it is in the expression if you look closely enough. Delta P, right, the change in momentum, can also be expressed as we did earlier. Delta P is just m times delta V. And so if we can solve for the change in momentum, we can solve for that change in velocity, or his final velocity, if we will. So even though you're not explicitly given V in the expression, don't freak out, right? We can solve for the velocity using our change in momentum term. So it looks like we're going to be trying to solve for delta P now, and then we'll do some work with that afterwards. All right, let's take a look at the momentum of Kelce before the collision. Let's see if we can get the momentums before and after to solve for delta P. I've given his mass and his initial velocity before the collision, so I'll plug those in, 118 kilograms, and then I'll be multiplied by 6.15 meters per second. That will be equal to 725.7 units of momentum. Then after the collision, I don't know his final velocity, but I do know his mass. So I'll just plug in 118 multiplied by, I'll just say VF. That's what I'm looking for, essentially. It's okay, you don't know it at this point. You can plug in a variable as a placeholder until we do. And I know that the momentum change here, delta P, I'm not really sure how to solve for that using the table, but what do I know, right? Delta P is just equal to that average net force multiplied by the impact time, or the time that they're in contact for. So even though I don't know delta P, I know what it should be, right? I don't know what it is from the table, but I know what delta P is given the resistive force and the time period. So I actually have enough information to solve for delta P here using a different method, impulse. So I'll plug in the values I was given. I'm told that this is a resistive force, and I know that in this scenario, this football player that is tackling Kelce is going to push against him, right? And so I know that this is going to be a negative 831 newtons. And again, the negative is just indicating that it's the opposite sign of his initial velocity. So in other words, this force is trying to slow him down or stop him. And so that will be negative 831 newtons multiplied by 1.30 seconds. And I should mention that a newton times a second will work out to be the same thing as a kilogram times a meter per second. So these are both valid ways of expressing units for momentum. They're essentially the same thing. That will be equal to negative 1080.3 units of momentum. All right, so now that I've solved for the change in momentum, or the impulse of Kelce, I can use this information in my table to solve for VF. And there are a number of ways that you can go about thinking about this. You can think that, well, if I started with 725.7 units of momentum and I, went down by 1080.3, then this quantity, right, 118 times VF, should be equal to that 725.7 minus 1080.3, right? If this was my initial momentum, right, the P initial, and then my change was this, right? This is my delta P, that will give me my final momentum. That's one way of thinking about it. You can also remember that the expression for any change in anything is just the final minus the initial, and that's how we've been filling out this table every single time, right? We take the momentum after the collision, and we subtract the momentum before the collision, and that'll work out to be the same idea. So I'll show it both ways here, just for example's sake, but realize that you can use the table a number of different ways to solve for the final velocity in this problem. If you use this first method, you would say then that the final momentum, right, is equal to that initial momentum plus that change, or in this case, the change was negative, so we'll subtract it. And then you would solve for your VF here. That would be equal to essentially negative 3 meters per second, or 3 meters per second in the opposite direction that Kelsey was traveling in the beginning. If you use this definition for delta P here, which you're free to do, you would also get the same thing. 118 VF is my final momentum minus the initial momentum, 725.7, is equal to delta P, the change, negative 1080.3. Recall that delta anything is just final minus initial. That applies to any quantity given a delta. Okay, so the same thing will apply. VF, you will get negative 3 meters per second once you add the 725.7 to both sides. All right, so once again, just application of the relationship between impulse, net force, and time. The table, again, really a helpful tool, even when solving impulse problems. So I highly recommend that you draw a momentum table when solving problems, at least at the beginning, to help develop a feel for what you're looking for. All right, this concludes the series of videos on impulse. Please take a look at Canvas for some additional practice problems to further develop your skills.